The pH scale. The pH scale is a logarithmic scale, and this was developed because the concentrations that we see or deal with a lot of times with acids and bases generating ions in an aqueous solution are very large orders of magnitude apart from each other. It can go all the way from, you know, 10, 15 molar all the way down to 10 to the minus 15. So this is a very large distribution in numbers. And a logarithmic scale will compress those down to something that runs approximately from about -1 up to about 15 in an aqueous environment. If you move outside of an aqueous environment, the pH is actually undefined, but you can still see people using the negative logarithm function to help compress the numbers down a little bit. So, briefly, pH is just equal to the negative log of the H plus concentration, or hydronium ion concentration. This is the formula that we typically use to calculate pH. It's not exactly the correct formula. pH is actually the negative log of the activity of the hydronium ion. Activity is very similar to concentration. It varies a little bit from it, and if you want to know more about that, you'll have to take an advanced class. This is a very good approximation of what pH is, and most people use this. It's only when you get into very precise electrochemistry that the other definition starts to matter. So how do we use the pH scale? Well, a neutral pH, as you might know, has a value of 7. And if we go higher than that, we would have a basic solution. And if we went lower than that, we'd have an acidic solution. So anything less than 7 is acidic. Let's see here, it's less than 7. And then basic is greater than 7. So, for example, a basic pH would be 10. An acidic pH would be 2 or 3. And then neutral, there's only one option for that. That's 7. So this can kind of orient where you are on the scale. Very strong acids will be at a pH around -1 up to about 1, depending on their concentration. If they're very concentrated, it can go to -1. One misconception is that pHs can never be negative. They can be. It just has to be a very acidic solution, and you don't often encounter those. And one of the other things with a solution that's that acidic, a normal pH probe will not be able to measure it accurately. And so it's more of you have to determine it some other way. And then if you move up to, say, lemon juice or acetic acid, just on its own, it will have a pH of about 2 to 3, because those are weaker acids. Our strong acids are down much lower than that. And there are a bunch of other weaker acids than that on our way up to pH 7, such as oranges and tomatoes and some rainwater that can be a little bit acidic. Then we get up to neutral solutions, which are water, or there are neutral salts that we can have. Human blood is a pH of 7.4, so that's just a little bit basic. And then seawater and baking soda are about pH 8. And then you start moving up to some actual stronger bases like ammonia and some of the other less soluble hydroxides. Those can be about a pH 10 or 11. And then your very strong bases can be all the way up from between 13 and 15. Generally, they don't go up too much higher than 14. And usually objects or solutions are not down to pH 0 that often. So that's just a little bit about the pH scale. Now, pH is not the only P calculation that you can do. There's also pOH, which is very similar to pH. pOH is, if you can take a guess, the negative log of the hydroxide ion concentration. This scale is exactly the opposite of the other one, of pH scale, where in this case strong bases would be a very low number and strong acids would be a very high number. And that's because the concentration of hydroxide is inversely related to the concentration of H plus in solution. The more H plus I have in solution, the less hydroxide I will have. And the more hydroxide I have, the less H plus I will have. And that just comes out of the equilibrium relationship, the K. So pH and pOH are actually not the only functions that we can put a P, or substances that we can put a P in front of. We can do it to whatever we want. If we wanted, we could say PCl, and it would just be the negative log of the chloride ion concentration. But these are the only relevant ones to an acid and base solutions. So we tend to focus on those. Here's one more formula that is quite useful when we're dealing with pH and pOH values. pH plus pOH is equal to 14. This comes directly out of the Kw expression. If we were to take the negative log of 1 times 10 to the minus 14, that equals 14. And then if we take the negative log of H3O plus concentration times OH minus concentration, we get pH plus pOH. Logarithms, one of their properties is they turn multiplication and division into addition and subtraction. And so that's where the plus sign comes from. This can be a very useful way to move from a hydroxide concentration to an H plus one, or back and forth. Or if I wanted to go directly from a pH to a pOH, I wouldn't have to first calculate the hydroxide ion concentration. I could instead take it from the pH, go right in there using this simple formula. And I tend to use that formula quite often.